Hi, Science 10. So in this video, we're going to be looking at the properties and patterns in the periodic table. Specifically, you got to know chemical and physical properties. Chemical, we'll take a look up there. That's sodium going into water, sodium metal going into water, blows up basically. So that's a chemical property. Physical properties, how things look, right? So, wires, well, that's metals, right? Metals are malleable, shiny. That's a copper wire right there. Non-metals, very different than metals, almost the opposite, really, right? That's bromine. That's some chlorine gas. So bromine's actually a liquid, kind of a steaming, weird-looking liquid. And of course, it all boils down to electrons. These properties, the physical and chemical properties. And those valence electrons, we can see right here that single outside valence electron that sodium has. Again, there's the charge telling you how many electrons it's going to give away. There's that single valence electron, and chlorine wants to take it. Again, it's charged -1. It says, hey, I want to take. And it'll stabilize. It'll stabilize them. They'll become stabilized like the noble gases, because the noble gases have that stable number of electrons. For helium, it just has the 2 stable electrons, but for neon, it's got 8 in its valence. And so basically what happens there is sodium becomes like neon in terms of its arrangement of electrons. And we'll be talking about that today, how electrons are arranged. Okay, so let's get underway. Let's share the screen. So real quickly in the course, we are still getting underway, but you've done already a lot. You'll be able to do the periodic table scavenger hunt, and then getting ready for the Chapter 1 assignment. You'll be next video will be looking at formation of compounds, which we've already talked a little bit about. Again, make sure you're in the readings, in our readings, but also the textbook. We're right here at about page 27. But yeah, let's get underway. All right, so this video, we got to know about chemical and physical properties, how reactive things are. And it starts to lead us into how to write the formulas for new compounds. We'll get that more in the next video after this. There's 3 major classes of elements in the periodic table. We'll look at those, 7 periods, and what does the period tell us? And 4 key groups out of the 18, and so groups 1 and 2 and 17 and 18, those are the groups we're going to be looking at. But let's talk about classes. Let's just get right into it. Let's look at the 3 major classes on the periodic table. And you can see your periodic table, which again, make sure you have in front of you. Make sure you've got your notes. We've got our metals, which are in blue here. So this blue area, all of the metals and their properties, shiny, malleable, ductile, they can be stretched into wire. They all conduct electricity really well. Metalloids are in between metals and non-metals, so they have properties of both actually. And of course, non-metals, some of them are solid, some of them are liquid, some of them are gas. They're very brittle. You can see how sulfur just kind of crumbles away. But yeah, here's your metalloids right there, some pictures of them. Silicon is a very, very unique metalloid. But yeah, let's get a few notes here right beside this. You're going to want to pause the screen and get all of this information down, but let's just take a few highlights for us together. Metals, they give away electrons. Your charge tells you how many. And if this is a review, write it down, right? Get it into your notes. The shiny. They can bend. They're bendable. They're good conductors. Okay, kind of on the other side of that, the opposite of metals are non-metals. So nonmetals take electrons. Again, write it down with me here. Think about it. It's those valence. The valence wants to balance itself out to make it like a noble gas. Well, instead of shiny, they're dull. Instead of bendable, they're brittle. And they really do not conduct. Whereas in the middle, the metalloids, I know we've got them on the bottom here, but they're truly in the middle of these two, right on the periodic table. You could kind of see there by the picture, the metalloids. Well, the metalloids have some of both properties. And semiconductors. So silicon is a great example. Our computer chips are made out of silicon. Silicon doesn't make electricity just zip along a wire like, say, copper. You can kind of see in my picture I've got a copper wire. But the silicon chips, you know, in our phones and in all of our technology control electricity. They do let electricity flow, but they can control that flow. That's really what a semiconductor, I know that's a fancy word, but ultimately silicon is a semiconductor. So sand, guys, yeah, that's cool, right? Can really control electricity. That's how computers work. That's, you know, our whole modern society. So that's you know, pretty darn important. Let's zoom out a little bit. Again, pause, you know, make sure to get the key information. Again, you know, your metals are all in this blue area. Your non-metals right there, you know, including the halogens. And yeah, the metalloids right in the middle. So, you know, that's going to be boron, silicon. Got to get the name of that one right there. Germanium, arsenic, antimonium, tellurium, polonium, astatane, all kind of in there as the metalloids, kind of a bit of both. And it makes sense for the staircase. Remember how the staircase divides metals into nonmetals. All right, so now let's look at the different periods, and they run horizontally. So period 1, 2, 3, 4, 5, 6, there's actually 7. But yeah, they run across. You can see here period 1 is just hydrogen and helium. But yeah, let's take a look at those next. All right, so in our notes here, periods run left to right. And they tell you something pretty interesting. You can see it written up there. They run left to right. They show the number of electrons, or sorry, the number of electron orbits. Let's take a look at the this picture here. You know, we've got not the whole periodic table, but kind of most of it in the first, pretty well all of the first 18 elements are here, and those are ones that you need to be able to draw models of. So here are those, actually up to the first 19 elements. Now look at the number of electrons, the number of energy levels though. Let's take a look at that. Let's look at the period number. Okay, here's our period 1. Look how many energy levels or orbits. 1. Period 2 has, look at each of these. You'll see it. Look all the way across. two orbits, right? Period 3, 1, 2, 3 orbits for sodium. 1, 2, 3 orbits, that's magnesium. 1, 2, 3 orbits, that's aluminum. Silicon's got 3. They're all in period 3. They've got 3 orbits. Period 4, make sure it's got 4. 2, 3, you betcha. That tells you the number of orbits. What this helps you do is arrange the electrons, right? Because it's only the valence that are involved in chemistry, but you still need to put the other electrons somewhere. And you'll notice there's a pattern there too. Take a look carefully at that first orbit. Always 2, always 2. Look at it here, only 2, only 2. Even there, only 2 electrons in that first orbit. Pause the video and just actually take a look at this. You need to be able to draw all of these, so you're going to want to make sure to start drawing them anyway. And again, looking at that third orbit, let's go over here to the noble gases because they're fully stable electrons. So we've got 2 in the first orbit. Count them up. 8. 1, 2, 3, 4, 5, 6, 7. Yeah, 8 in the second orbit. And third orbit? 8. 2, 8, 8 for electron arrangement. But yeah, that period shows you exactly how many orbit levels that there are. So let's just finish our little notes here on the side because you've taken a look. So period 1, 1 orbit. We also call it an energy level because electrons have energy. Period 2, 2 orbits. Period 3, 3 orbits. We get the pattern. The next critical thing is knowing about and understanding and being able to draw the arrangement of electrons because they are arranged in a specific, predictable pattern, you know, really for the first 18, I guess 20 electrons here. Make sure you can definitely draw those first 18. Energy level 1, 2 electrons. Again, confirm it in the drawing up there. Energy level 2 has 8, or should have 8. And a reminder, say for aluminum here, it doesn't quite have those 8 electrons. 1, 2, 3, 4, 5, 6. Oh yeah, no, it does. Sorry, it's in its third, so it does have that in its second. But in its third, if we check its third, should have 8. Check that out. It's only got 3. And so it just gives those away. You know, that's not very many. That's not very close to 8. So it's going to give those 3 away. And check out the charge on aluminum, 3+. So literally, that's what that plus sign is telling us, that, hey, those 3 electrons in my valence, I'm going to give them away. Only the noble gases have this. Definitely write that down. You know, this specific, and of course that first one, I mean, that's helium. And again, check it on your periodic table. Helium's got those 2 electrons. 2 and 8 is 10, so that's neon 288 that equals 18, right? So that's argon. And yeah, those first 18 we definitely need to know. All other atoms / elements, you know, when we're talking about properties, this will give them not only their physical, but their chemical properties. All other atoms, elements, not electrons, sorry. Have an unstable valence, an unstable outside electron shell. And yeah, they're trying to emulate the noble gases. Noble gases are stable. Everyone else is unstable. And that gives us chemistry. Last point we want to put here about the valence is the charge tells you, not your, tells you, tells you to either give electrons if it's a positive charge, and of course how many, or if it's a negative charge, it tells you to take, again for the valence. And of course, which ones have the positive charge? And you can see that on your periodic table. The ones with the positive charge are your metals. The ones with the negative charge are the non-metals. Okay, groups. Let's look at groups. We understand what periods are. Periods ultimately show you a number of energy levels, show you where the electrons are specifically, how they're arranged. But let's look at groups. What do groups show us? What do groups tell us? So groups, they're vertical. Okay, they run up and down. Some key ones, group 1, group 2, group 17 right here. Those are really the four that we need to know. Group 1, alkali metals. Let's write this down. Okay, get this into our notes. Group 1 are the alkali metals. So that's their name. Well, that's cool. Group 2. You'll see group 1 doesn't include hydrogen. Hydrogen's quite unique. And so group 2 are the alkali earth metals. Now there's a reason why they're called alkali. Alkali is another word for basic or alkaline. And essentially what that means is when these metals are in water, what they will do is they'll actually, especially if they go into water in their pure form, they'll end up kicking hydrogen out of the water. And then essentially the water is going to end up having a lot more hydroxide, which is basic. We'll be talking about that with acids and bases, but just a little hint of what's coming. We know that water is H2, 2 hydrogens and O. What alkali metals do is they actually kick the hydrogen. That's why we saw that big explosion there with the alkali metals. Also in the notes in our readings, you got some videos to watch, specifically really about the alkali metals and also group 17 to show you some reactions. So you have that image in your mind of their properties. And group 17 are called the halogens. These are really the four you need to know. I know we've got groups 3 to 12 transition, but these are the four you've got to know. And group 18, well, we know those, the noble gases, or inert, meaning they do not react. Now, why was that again? Why did group 18 not react? Stable electrons, stable valence electrons. They followed that stable pattern of either 2 in that first orbit, helium, right? Or 8 in their second, well, that's neon. Or in the case of argon, it's got 8 in its third, 288. That's Argon's phone number, phone for stability. Now those are the four that you got to know. Here's what you got to know about their properties. So get this information into your notes as well. I'm going to talk you through it, but you've got those four things written down, but you're going to want to get the properties of the alkali metals. They're shiny, they're soft, you know, it's lithium, sodium, potassium, rubidium, cesium, francium. Shiny and soft. They got low density. They'd float on water, but you know they're so violently reactive, it's hard to tell. And yeah, they corrode or form oxide coating just in the air from oxygen, right? And that's basically, watch some of the videos. You'll see that happen literally in real time. That can cause water to explode in fire. And that's the hydrogen being kicked out, being violently broken out of the water. Don't even put acid on them. And yeah, that's where group 1 is, all the way down there. Group 2, alkali earth metals, beryllium, magnesium, calcium, strontium, barium, radium. They're shiny, but they're harder, just reactive, as opposed to violently reactive. They'll react with weak acids, and they're going to release hydrogen. We'll see little bubbles, and we're gonna do an experiment. You're going to get to watch an experiment like that, and see what happens specifically when magnesium is put into weak acid. Group 17, the halogens, so francium, chlorine, bromine, iodine, astatane. Some are gases. One's a liquid, it's the bromine. Some are solid. You'll see that on your periodic table. This is just kind of a model of the periodic table. These are violently reactive as well. They'll easily react with any metal to form a stable ionic, that should say ionic, compound. Ionic compounds are always solid, their state of matter, and they're always stable. And coming from very violent, something very, very violent. Group 17 are all diatomic. F2 gas, that's how fluorine exists. Chlorine exists, Cl2 gas. Bromine, check it out on your periodic table. Take a look at where bromine's at. Good old number 35. You'll see it's Br. Notice its state of matter. Br2, because it's in group 17, it's a liquid. Look at iodine, I2. Check out its state of matter. Again, number 53, solid. They're all diatomic. That's how they stabilize their valence electrons. They're so violently reactive. As long as there's a bit of fluorine together, they're going to form up in a gas. Somewhat stabilized, still incredibly, incredibly dangerous. Last, group 18, noble gases. Well, they're gases. Helium, neon, argon, krypton, xenon, radon. They are inert. They do not react. So yeah, these properties. Why do these groups have these properties? That's what we're going to look at next. Ultimately, yeah. It's the valence electrons. It's the outside electrons. It's all about the valence, all of that. All right, so let's take a look. The slide, yes. Okay. Just want to zoom in on it for you here. Your valence is the outermost occupied energy level of an atom. I mean, ultimately, what you got to do, guys, is you got to look at some of the models that we've done together and get comfortable drawing your model of the atom. You take a look at the charge for each atom in any of the groups. Start with group 1. What do you notice? So looking at that charge, you notice it's all +1. All give away 1 electron. It also tells you about the valence electron. It tells you that there's 1 valence electron to have. So let's just put this info down. So group 1, they have 1 valence electron. That's a pattern. 1 has 1. Group 2 have 2. Oh, this is interesting, right? Group 13, because again, looking on our periodic table, I know you got it in front of you. So looking at good old boron here, right at the top. All of those in group 13 have 3. Group Group 14 have 4. Group 15 have 5 valence electrons. We're going to come up to group 18 is going to have 8. So you're already seeing the pattern. Group 16, 6. Group 17 have 7. And group 18 have 8. Let's check that out. Also, we're going to need to be able to draw these models that we're going to see next. So let's check this out. Okay, so we're going to draw just the valence electron of the first 20. You need to be able to do them. We're not going to do all 20, obviously, together. This is them done here. Again, you know, your groups running up and down. If we're just drawing, just representing the valence electron, and it starts to make you kind of feel that, oh yeah, they're going to want to give that away. They can't quite hold on to that. So yeah, so let's draw a few of these together. They're called Lewis dot diagrams. Okay, so in our notes, draw valence electrons. Use your periodic table to find out how many, and literally your group number simply tells you. So just look at the group number, and let's start with lithium, and I'll put my periodic table right beside me here, and lithium has just got a single dot. Okay, let's do a few more in group 1. Sodium, it's just got a single dot. That's its valence electron, that little dot there. Let's do potassium, single little dot. Let's do magnesium. Couple little dots. Let's do calcium. Again, just a couple little dots, 2, because they're in group 2. Again, representing the fact that they can give away those 2 electrons. Let's jump over, go across the staircase. And let's go right to carbon. Carbon is very, can bond to anything. So carbon is in group 14. Therefore, it's got 4 valence electrons. And at this point, it's not going to give those away because we're getting close to, you know, our noble gas. You know, if we go over and you know, we're on period 2 or period 2, group 18 is neon, right? And neon, group 18, it's got 8. So it's got a full, it kind of all stabilizes. This is where this starts to fall together. When you start comparing, you know, your noble gases. So, you know, they've got that nice full valence, nice and stable. Carbon, with its 4, it needs to accept another 4. For example, hydrogen will easily link up, and in fact, that's methane. When you take 4 hydrogens and link it up, because carbon is going to want, let me just do this so that it's transparent. Carbon is going to want to fill up its valence. It's going to want to become like neon, so it's going to need 4 of these, right? So we'll just copy this and just kind of quickly. Now, they're going to kind of be on the side, so they won't quite look like this. They'll look more like that. There we go. This is literally how methane forms. What happens to the valence of carbon is it starts to act like neon, and it stabilizes it. Anyway, let's undo that just so, because we're just going to do those Lewis dot diagrams. That's what they're called. Well, we got neon. Let's do the noble gas right underneath there. Well, actually, we'll do helium above it. Helium. It's got 2. Remember, in that first valence, that's stable. Is 2. In that first period. In that first orbit. Let's look at argon. Again, group 18, therefore it's got 8. We call that also an octet. So that octet, or 8, it wants to have 8. It either wants to, in the case of metals, if they give them away, then they're gonna underneath their next shell of electrons is going to be 8 underneath. Okay, now think about that, what I just said, right? So remember your model for sodium. Okay, just looking at the sodium atom, it's got 11 protons, it's got 12 neutrons. Okay, and then we got 2 electrons there, we got 8 there, and just the 1 electron. Again, that's what the Lewis dot diagram shows. But if we lose that one, oh yeah, see? If we lost that one, say over here to, well, it would maybe be, it might be, say, chlorine, which I don't have drawn just yet, but ultimately it's going to have its 8. It's going to suddenly feel like it's become a noble gas. It's going to feel like it's kind of like neon and argon. It's got those nice 8 electrons. Okay, actually, let's draw a few of group 17. Group 17, well, they have 7, right? So fluorine, 1, 2, 3, 4, and this is how we set them up. This is how we arrange them. 1, 2, 3, 4, 5, 6, 7. Ah, there's a space there. It can accept. How about chlorine? Well, it's also group 7. Not group. It's also, yes, it's also group 17, and it can therefore have the 7 electrons arranged in the same way. Oh, there we go. So this is why sodium loves to link up right there. Boom. Now look at the chlorine. It's looking just like argon. It's looking just like neon. If you take a look carefully at what's happened, once you form that nice stable sodium chloride, those valence electrons, it's matching the noble gases. Now the other way, though, that this group 17, and again, remember how violently reactive these ones are. Let's do one more. We'll just do those 2 actually. What they do is they have to link up with another fluorine atom, for example, or chlorine has to link up with another chlorine atom, and to help stabilize their valence. And essentially what they end up doing is sharing an electron. And so if we take 2 chlorine atoms, and we've got our valence here with 7. Oh, okay, so this is why they like to bond together. This is why it exists as Cl2 gas. Same for fluorine. Fluorine cannot exist independently. If it's independent, in fact, that's what a spark would do. A spark would break this apart, and then the chlorine, I mean, it just would literally explode. And the same with fluorine gas, just a tiny, tiny, tiny spark, which could even just be exposure to water or something, could literally be enough to essentially light it up. But there we go. We've got fluorine right here. And again, you can see group 17, it's got 7 valence electrons, so not quite like a noble gas. You know, a reminder, your noble gases are nice and stable. There's their valence, nice stable valence number. Fluorine, well, there we go. If it does that, suddenly they're quote unquote stable. They're still highly reactive, in fact super reactive, but at least somewhat stable. Lewis dot diagrams, you got to know how to do those for all of the first 20. So, you know, practice this, hit pause, use your periodic table, And you know, for example, nitrogen is group 15, right? If nitrogen is group 15, therefore it's got 5. Same with phosphorus. Carbon is group 14, therefore it's got 4. Notice those patterns. You'll start to see those patterns. And of course, helium's only got the 2 electrons. That's why it's, and of course, in its first energy shell, you should have 2. All right, science 10. So that's how to do Lewis dot diagrams. And ultimately, this is why you know, chlorine exists as Cl2 gas. This is why hydrogen exists as H2 gas, right? A couple hydrogens get together. So you got one with its 1 valence electron, and you get another hydrogen right there. Boom. They can share it up. Let's take a look. This is something you need to know when you want to write on your periodic table. All of the atoms that are diatomic, right there, write these on your periodic table. H2 gas, N2 gas, nitrogen, oxygen, of course we know that, fluorine, chlorine, bromine's a liquid, iodine's a solid. Also know phosphorus is S8. Yeah, that's cool, right? That's to stabilize its valence. And that's something very unique about phosphorus. It needs to get 8 of them together. Sorry, phosphorus, sulfur. Got to read my own screen. Sulfur is S8, solid. Phosphorus is P4. Why are they this? Well, they're stabilizing their valence electrons. It's just how they need to be. Everybody else is monatomic, right? All of your metals. So we say, and you read any metal, look at, I don't know, this one, titanium, TiS. It's not Ti4, it's not Ti20, it's not Ti2, it's just a single atom, whereas these ones have to exist as 2 atoms or a diatomic molecule, right? Molecule is 2 or more atoms bonded together, but we only have the 2. Well, it's a tiny molecule. And why are they doing this? Yeah, it's all about the valence electrons. Hydrogen is trying to make itself kind of like helium. Nitrogen is just kind of trying to balance itself out, sort of trying to act a bit like neon and the noble gases. Same with oxygen, same with fluorine, same with chlorine. All right, science 10. So this one has been on patterns and properties in a periodic table. Take care.